Okay, so without further delay, I'd like to resume the meeting. And next speaker is Dr. Pinaki Mazumder. I know him from University of Illinois days. When I was a faculty member, he was a very, very bright graduate student who knows everything. And after graduation, he went to University of Michigan, Ann Arbor. Has a very broad industry experience as well, memory design, you name anything. And then recently, he has been program director at National Science Foundation. And he is the one who sponsored this symposium. He encouraged us to write a proposal, so I did. And then he made sure that went through the right process, and I was fortunate to get approval from his office. And he is going to give a presentation. I initially wanted to have him opening remarks, but he prefers as a professor to give a technical talk. So he will give a technical talk beyond CMOS and evolutionary computing. Pinaki, thank you.
Thanks, Steve. As you can see from the picture that, I'm shuttling between National Science Foundation and University of Michigan. I'm with the Computer Science and Engineering Division over there. So as I shuttle, I just collect more frequent flyer. But otherwise, I get paid only by one institute, that is university, and I have 2 masters to serve. So just to give the overview that, over the last 100 years, you have seen that there is an exponential growth in terms of computational power. We talk about Moore's law, which is the generation 5 for the integrated circuits, and which you have seen that the integration density for transistor in a chip has increased exponentially. But if you go look at the historical evolution, I mean, even with the electromechanical relays, vacuum tubes, and transistors, this exponential growth has been the scenario, and that's why there is this tremendous computational resources we see now. And it has also economic impact. The law of accelerating returns by Ray Kurzweil, it kind of captures this whole evolution of computational power and its impact on economy. So in order to sustain this economic growth, obviously after the red brick wall, which we have been talking about for last 10 years, but nobody has seen that yet. So what will be the next generation electronics or the devices which will enable us to enhance the computational speed beyond what the CMOS can do? Obviously, CMOS people have taken care of it to a great extent by introducing this multi-core. And multi-core now, you have seen, is growing exponentially. So that's kind of a another Moore's law within the context of integrated circuits. But we are looking into the technologies which will be enabling us to design things in a more revolutionary way, as well as the integration density would reach much larger. And in the context of Memristor workshop, we see that, this is pretty, that's one of the goals of the Memristor devices, to answer these questions. Can you attain exponential computational speed through revolutionary architectures and disruptive technologies with new device transportations like quantum tunneling, ionic transportation, plasmonic, and various others? So I will just talk about a few things that our group has been doing. This is just to give the Intel picture. Intel has been very aggressively scaling the CMOS devices, and probably beyond 32 nanometer, they will be able to even introduce 22 nanometer CMOS devices. But then within the scaling group, there are some amount of skepticism whether CMOS devices itself will be reliable enough for beyond than that. That's why over the past several years, the different types of technologies like carbon nanotube, graphene, and all has been being pursued to see that whether that can enhance the speed at the beyond 20 nanometer. But in terms of application, there won't be a dramatic change because of the fact that this will still use the Boolean switches and von Neumann type of architecture. So this is what we call evolutionary architecture. And since the industry is much better equipped than we folks in university, that's why we are looking for some more revolutionary type technologies and architectures. So in terms of concept, in the evolutionary architecture, we see that computational paradigm and methods are Boolean logic and simple circuit equation, as opposed to in revolutionary circuit, we have nonlinear dynamics and differential equations. Architecture, mostly, we still use the von Neumann load store architecture, even though there are other types of architectures that are also used in the CMOS, using CMOS. But because of the fact that most of these nanotechnologies have the driving problem, that's why the local computation, neuromorphic computation, or cellular automata type of architecture is being sought. And you have seen in the morning, there are some applications for Memristor for neuromorphic applications. Chip fabrication technology, the DNA self-assembly nanotechnology for lower than 20 nanometers or so are being pursued. Programming methodology, instead of standard instruction fetch and execution, these will be mostly templates-based, depending on the interactions between the different processing element within a sphere of activity, and local interconnection. Complexity and versatility are the main problem. The von Neumann architecture is general purpose, and one can use it for various applications, whereas these applications involving local computation often becomes very task specific, and they are very homogeneous. So with this difference in mind, we have been searching for the candidate technologies for the future. You have seen spintronics, then nanomechanics, then nanomagnetics, and DNA also. People have been using DNA computing or biocomputing. We have been looking into 3 different candidate technologies. One is quantum tunneling, which is obviously the precursor of transistors. We know that Esaki diodes have been there for a long time, but because of the monolithic fabrication and integration issues, and also in the past at Bell Labs, there are some work done. The problem is that most of the 2-terminal devices didn't have the isolation and the driving capability. So those are the issues. That's why it really did not make a huge impact. So now we are seeing that using the quantum tunneling transport, we can do a lot of stuff. And I will just talk about a little bit about that. Our group has done a lot of work about it in the past. We are also looking into plasmonic as a possible way to enhance the speed, as well as mostly the speed, because of the fact that at optical frequency or at terahertz frequency for spoof plasmon mode, you can make different types of devices. Most of the applications right now are for the passive devices, but we are now looking into structures which will enable us to make digital logic with the active type of device, actually. Then this is what you have heard in the morning. I will also talk a little bit about that. I have a colleague, Professor Wei Lu, who used to work with Lieber at Harvard. He has been in Michigan for the last 2.5 years. So we have been working on working together. And we also have developed amorphous silicon-based Memristor circuitry. I will talk about that a little bit also. So first, let me talk about this quantum tunneling transport. So in terms of, the Memristor is mostly the monotonic nonlinear device. And we are here, we'll talk about the non-monotonic devices with the hysteresis characteristics and the advantages of that. So over the past 25 years, you have seen that the silicon integration density has increased because of several milestones. The local interconnect has been replaced by highly conductive salicide materials. Then the global interconnect, the aluminum has been replaced by copper and low dielectric materials, and also bulk materials also to improve the parasitic effect and all has been replaced by insulating material, silicon on insulation. So this work we started about 10 years back under a DARPA project to see that in order to enhance the frontier of the VLSI technology, what else could be done. So our approach was that, so most of this thing has been accomplished by scaling, and by virtue of that, the basic switch characteristics remain the same, as you could see in the, there is no laser pointer, is there a laser pointer? Thank you. So as you could see that, this IV characteristics remain same both for potential effect as well as the field effect devices. And so up to this, we have mostly taken advantage of that. So in 1997, when we started looking into some of the disruptive approaches to enhancing the cost per, improving the cost per device performance as well as the delay power performance, we thought that if we could you could bring forth the quantum transportation such that the IV characteristics can be changed to this type nonlinear characteristics, that will enable us to design circuits which could be much more compact, faster, and so on. So there has been tremendous amount of effort was put at that time to create different types of material structures, silicon dioxide sandwiched between silicon. So these are mesoscopic structures. Here, because of the fact that there is a quantum well where there are discrete states, and because of that, this device, I just don't want to go through all the details, this device behaves like a negative differential resistance device. And so we could see that we could bring quantum transportations on silicon, and there are a whole bunch of other materials that have been studied at that time by a consortium of some 4 or 5 universities as well as Texas Instruments at the time. And we could then actually build these devices on CMOS, and our group mostly looked into the different applications of that, and as well as the CAD tools which are required to design circuits with this type of devices. So some of these things were the modeling, how to capture this modeling in SPICE, and because of the the nonlinear, this type of non-monotonic characteristics, the Newton-Raphson's algorithm failed, so how to take care of those problems. So we have done quite a bit of work in the past with the idea that it's not just over CMOS. You can build this technology over 3-5 materials like gallium arsenide, indium phosphide, antimonide-based things, silicon germanium, as well as the molecular scale also. This is the read-to structures, molecular structures, which also gives the NDR characteristics. There are other types of molecular structures like buckyball, or for that matter, BPDN, also gives this type of negative differential resistance characteristics. So this opens up a huge opportunity to re-examine the circuit design from a different perspective, and that's what we have done at that time. I'll just give a very the gist of the advantages. So because of this nonlinear IV characteristics, we could now, we have the built-in flip-flop characteristics with each of these gates. So we could build extremely fast different types of adder circuit, arithmetic circuits. And these are the different designs which we have demonstrated on CMOS, that how we can enhance the performance of CMOS using the nano pipelining feature, as well as incorporating a pair of diode at the pre-charged nodes of different types of single true-phase flip-flops, such that you can enhance the performance, improve the noise margin. Then in dynamic logic, also we incorporated these devices to make a good trade-off between the noise margin and the speed. So for keeper circuit, usually instead of using the standard PMOS keeper, we have designed different types of patented circuit techniques actually. Similarly, in memories also, in order to replace the refreshing operation, which actually takes about 3.6 picoampere current per cell, we could actually reduce that by 1,000 times. So there are a whole bunch of strategic advantages which we have shown of this nonlinear IV characteristics of these devices. And also we have designed the multi-valued logic, both programmable gate arrays and so on. Then Professor Chua, he listened to one of my talks in around 1998 or so, he told me that why don't you look into some of this cellular neural net in the area of cellular neural net. And initially, I was not sure that how much advantages we can accrue. But then we found out that definitely by taking advantages of this nonlinear IV characteristics, we can make the processing elements much more compact. As you could see that the CMOS versus the with the mesoscopic structures like this, the RTD type of structure along with NMOS device. And we have demonstrated different types of image processing applications with this. Here is an example where you can see the extraction of the image over here on the smoothing operation. So we built different types of cellular neural network circuitry using both quantum MOS as well as other technologies. Then we started looking at, we have been funded by Office of Naval Research, and Larry Cooper, who was a big an ardent supporter of this type of technology, he asked me to look into at the quantum dot level, which was more difficult because now you have, instead of RTDs, which are 1D confined, these are 3D confined devices. So we spent some time, and we built also using a NERT grant from NSF, where our group does not do the fabrication. With other partners, we have fabricated quantum dot based image processing circuitry, and these are some of the IV characteristics of this, and these are some of the parameters of that. So again, what we have demonstrated that for using this type of quantum dot, and by creating different types of interconnect pattern, which could be resistive, capacitive, or some other tunneling type of devices, we can get different types of 2D filtering operations, and these 2D filtering operations are pertaining to some of the image processing functions like, say, edge detection or vertical or horizontal line detection and so on. And after that, we looked into more complex type of transfer functions where we not only could detect the static images, but also the dynamic images like this for motion detection. So for that, we have now spatiotemporal transfer functions, and we have been working on these type of techniques to show that how we can take advantage of this non-monotonic characteristics of these devices, and by creating approximate the different patterns, we can do that. Then I'm working with some groups who have been using the DNA nanotechnology to basically self-assemble the structures. How much time do I have now? Okay, another 10 minutes. So I will just quickly go through this ionic transportation based devices. This, as I mentioned, Wei Lu, he was working with Wei Lieber, and he has been at Michigan for 2.5 years. So his approach is a little different, even though amorphous silicon may not be the best material, but it also has, we have demonstrated that we can get very good performance, just like you have seen with the titanium oxide between platinum. In our case, we use silver and polysilicon and crystalline silicon, actually. So we have also tried to develop some crude modeling of the transport characteristics, because these silver ions, they get trapped in the amorphous, in the defects of the amorphous silicon materials. So since our group does a lot of tunneling type of characteristics, so we are trying to characterize how we can model the IV characteristics of these devices. And again, our group did a lot of work in memory area, so that's why we started looking into the memory application. And Lou has made 8x8 array, and we could store different patterns in that, and we are trying to make much larger array with this amorphous silicon. So this is one of the patterns which has been stored and tested over long duration of time, whether in terms of the data retention capabilities and all. So what we find that in terms of the IV characteristics, it is not as good as you have seen with the other materials. Actually, in our case, we need a slightly larger voltage, but we have been working on in terms of improving the devices and all. So here you can see the in terms of the non-volatility aspect as well as on-off ratio. Again, for you know, the off ratio tends to deteriorate over time. So that's the main problem in terms of the memory application. So right now we can see that we can get 10 to the power 4 operations over a period of 160 days or so, the retention part. Now, as in the morning, it has been pointed out that the interest in this type of MIM structure, metal insulator metal type of structure, has aroused, was spurred by the fact that they have the non-volatile memory capabilities. And over the past 10 years or so, there are a whole bunch of different combinations of materials have been studied. The main thing is that, you know, how a good trade-off between on-off ratio, endurance, power consumption is also an important factor. The endurance cycles, out of all the materials that we have studied so far, actually not studied, the compiled from the literature, we see that with ours we get about 10 to the power 6, which is the highest. And in terms of power consumption also, we have optimized these devices to have to reduce the power consumption considerably. However, 10 to the power 6 is not really, you know, good enough for dynamic memory or for solid state disk type of applications, but at least it could be a viable candidate for flash memories, because flash memories have typically 10 to the power 6 endurance or so. But we believe that, you know, this is at a very elementary and early stage actually. After doing lots of device studies as well as characterizations of the transport and all, we should be able to increase this. Whether it will go to 10 to the power 12, I doubt, but at least, you know, by another order of magnitude, we should be able to improve that. So it still, you know, stands as a very good viable candidate for NAND and as a replacement to NAND and NOR flash, even though of late NAND and NOR flash also has made considerable progress in terms of the sizing of the device, and still they are at least 2 to 4 times bigger than these type of crossbar structures. So this is one of the applications. Another applications we are looking into, as you have seen from the Hewlett-Packard presentation, is in the area of neuromorphic computing. We know that, you know, since the days of ENIAC and UNIVAC, the perceptron computers were considered as a means to do the neural computing, to recognize patterns, to classify. But the integration density in those days were so small, so that's why perceptron activities did not move much faster, much beyond than few feed-forward networks. Then in 80s, when Hoffield had demonstrated that you can do traveling salesman's problem on a silicon chip with about 1,000 neurons integration, then it kind of rekindled interest, and a whole bunch of work done under the DARPA project and other efforts. But then over the past years, different people have used CMOS and other type of existing technologies to increase the density to 10 to the power 4 to 10 to the power 5. But then still, in terms of the capability of mimicking the brain of even a lower order primate, it is not sufficient. So in order to do that, we need 10 to the power 8 to 10 to the power neurons. And that's why this Memristor-based crossbar structures are considered to be one of the very interesting thing. As a matter of fact, our group has done in the past a lot of work in applying this type of structure to make VLSI chip self-repairable or self-healing capabilities. So we have developed structures for memory automatically to repair memories, to processor arrays and all. and some of the issues that Snyder has mentioned, that the robustness of these circuits, that if there are sporadic number of defects because of the fact that they use the collective computation capability, so they are pretty much robust in terms of the different types of synaptic stuck-at faults, bias. We have studied quite a bit about that. So with this in mind, we have started working on, with the help of other groups, to develop neuromorphic circuit using Memristor. And since it is a chicken and egg syndrome, first you write a proposal to get money to make a build system, big systems like that. So we have been actually writing quite a bit of proposals of late to develop some sort of larger neuromorphic circuits, which will be having the reasoning capabilities and things like that. But again, at this point, it's just at the proposal phase, and the work will be, right now we are mostly working at the lower level, circuit level, but as the big systems, if we get money, we'll do that. Now the last thing, do I have a few more minutes? Few more minutes. Okay. The last thing I'll talk about is the plasmonic, actually. I'm intrigued by the capabilities of some of this, this plasmon transport, the kind of circuitry we can make. Basically, what we see is that in one side we have the dimensions of electronics, in another side we have the speed. So in terms of speed, the photonic devices operate at terahertz frequency range, and the electronics, nano-electronics, they can go up to 10 gigahertz or so. But in order to integrate both photonics as well as the nanoscale, CMOS, and other types of devices, we have to have some sort of a bridging technology, and that's where this plasmonic comes, because of the fact that they have the nanoscale dimension, but at the same time, they can operate at the optical and terahertz speed. So in order to create a dialogue in a hybrid structure like this, which will be the future generation VLSI, where you will have the convergence of communication, then computing, as well as some of the consumer electronics type of mixed analog circuits and all. So we need some techniques so that the photonics signals can be processed by the electronics and all. So with this idea, we started looking into that. So we started mostly looking into most of the passive structures, actually. And so basically, if you have, at Stanford and Caltech, they have done a lot of work in this area in terms of actually building these devices. And then we got involved in terms of modeling these devices and how to make circuitry using this type of devices. So if you have a chain of nanoparticles, and if you excite one of them photonically, then the free electron starts vibrating, oscillating, and because of the oscillation of the free electron, it creates the electromagnetic quasi-particles plasmon, and this plasmon then gets coupled to the next one, and that's how you can pass the signal from one end to another end. This is occurs at both optical frequency as well as at a lower frequency, the terahertz range, actually. So this is the demonstration of that. We have developed the modeling so that we can introduce them in SPICE, such that we can integrate both the electronic and the optical components together. So our group does not do the fabrication, but we are mostly working towards the modeling and application of these devices. This is another application where the nanowire, how the signal propagates over a nanowire. Again, the nanowire is MIM structure, metal and insulator. At the interface, you can see that here, you have metal, gold metal over here surrounded by dielectric, and the opposite also you can do that. You can have dielectric wire surrounded by metal, and basically we can see that we can propagate the signal at near optical frequency from one end to another end. So again, this plasmon transportation is very effective to connect the optical component with the photonics component. So these studies we are doing, we are developing the SPICE model for that. And then we are looking into some of the interesting applications. These are some of the applications which other people have done, and we are trying to develop the circuit models for that. So if you have a parabolic set of nanowatts and you excite one of them from one end, then it optically just illuminates, and then it focuses at this point, and then the signal gets coupled to the waveguide over here. So these type of very, very esoteric and different type of circuitry which we cannot do in silicon, we are studying those kind of stuff actually. So I will skip all the other stuff. So the main idea is that we have studied different types of passive components, and now we are looking into the active components such that in the future we can build circuitry which will meet the goal of the Moore's law, that we will be able to design different types of architecture and all at a very high speed. Okay.
Thank you. So due to lack of time, we will entertain a question maybe during the break, but okay. Otherwise,
I'm sorry,
thank you very much.
No,
That's thank you. Thank you. So while we are changing computer, let me introduce the next speaker.
I tried to make it 30 minutes.
It's Professor Wolfgang Porod from University of Notre Dame. And his talk is going to be Memristors, an interest observer's perspective. And Professor Porod is the endowed chair professor at Notre Dame. Frank M. Freiman, professor of electrical engineering. He earned his PhD from University of Graz in Austria. And his areas of interest include solid-state physics and the application to solid-state electronics, especially reliability, degradation, breakdown, quantum devices, and the architectures for nano-electronics, and then physical limits imposed on computation. So thank you. Let's begin.
Thank you very much. Thank you, Steve. It's a true pleasure to be here. I've been, as you have heard, I've not really worked in the area of memristors per se, but I've been an interested observer, so I would like to make a few comments about this technology. I've been fortunate enough, however, to work with Professor Chua on funded projects for more than 10 years now, I believe. And so I view this symposium really as a celebration of Professor Chua's long-time work and long-time contributions. All of you know, of course, about his contributions in the area of memristors and the work that it has inspired. But some of you may not know that Professor Chua has conference series based on the work that he has done. There's a nonlinear circuit theory conference in Europe that has been going on for more than 15 years now, which is based on the pioneering work that he has done, and Professor Ernest Koo here from Berkeley. Another conference series is based on his pioneering work in the area of nonlinear networks, so neural-inspired architecture, cellular neural networks or cellular nonlinear networks. CNN, Professor Mazumder referred to that briefly. And this is also part of our collaboration. So Leon, it's really a pleasure to be here. And I think what we might see in the making here is yet another conference series, which is based on, on your work. So I would like to comment on essentially two aspects of memristors. We've heard already that memristors might act as switching devices, and I'm going to make some comments about memristors as switching devices in the context of the semiconductor industry's search for a new switch. I'm going to say a little bit about the Nano-Electronic Research Initiative, NRI, which is sponsored by SRC at this point. And then a second set of comments is going to be focused on cellular nonlinear networks, some of the collaboration that we are engaged in right now, and some prospects that I see for CNN in this area. So let me start out with the SRC NRI, and in particular, you may have seen on the first slide, I showed you a logo for MIND, which is the new Midwest Institute for Nanoelectronics Discovery. It is a fourth SRC center, which is hubbed out of Notre Dame. The NRI, broadly speaking, has grown out of the concern of the semiconductor industry as silicon, Pinaki was referred to that, is running into some roadblocks. And some of the major technology companies have formed the NRI, the Nanoelectronics Research Initiative. And so the charge of this research effort is to look for a new kind of a switching device, or at least look into the possibility of a new kind of switching device. And so just to briefly tell you about the landscape of this effort that's going on in the United States, at least. The first NRI center, Albany, on the East Coast with IBM strongly behind it, was started about 2 years ago. A little bit after that, the second NRI center, WIN, the Western Institute for Nanoelectronics, is hubbed out of UCLA and USC, also with Berkeley participation. Intel is the company behind that. About a year and a half ago or so, the third NRI center in Texas was funded, the Southwest Academy of Nanoelectronics. And then just about half a year ago, we started a Midwestern center at Notre Dame. So part of the work that's going on within MIND is to look at different kinds of switching technologies. I'm not going into all the details here. If you're interested in what's going on in detail, I can certainly talk about that. I would just like to mention that we're looking at lateral tunneling transistors. Alan Seabaugh, who joined us a few years back from TI, Raytheon, is looking at these new kinds of tunneling technologies. And then what's most relevant to what I would like to talk about here is an architecture benchmarking effort that we are engaged in as part of this MIND center, together with my colleagues Mike Niemeyer and Sharon Hu in computer science and engineering. So the motivation of this benchmarking, which is going to include the Memristor, and that's where I'm going here, is to review all the kinds of technologies that are being pursued at this point under SRC NRI support, and to try to benchmark these different architectures from one common viewpoint. And so the kind of approach that we are taking is that we are not only going to evaluate these technologies from a basic device point of view, in other words, a new switching device that you might conceivably drop into existing FET-based architectures, but we're also going to look into the opportunities that these devices might have on the architectural level. So maybe one can perform a given function in a different way with the new kind of physics that you might deploy into new types of devices. And so we have come up with a spreadsheet. I'm not going to go through that in detail, but we've looked at relevance criteria like scalability, performance, of course. Again, I'm not going to go into all of these details, reliability, and then what's important is to look into CMOS technology compatibility, but also into the architectural compatibility. We are not only looking, as I mentioned before, at replacement switches, which are going to drop neatly into existing architectures, but we are looking into a different kind of architectures, which you also heard from the HB group before. So we're looking at heterogeneous architectures and also what's called as morphic architectures, ones where sensing and computing and information processing and perhaps also communicating are, where all of these functions are being merged, I wanted to say, and the And this cellular nonlinear or neural network architecture that Professor Chua has pioneered is an example of that. You heard Stan Williams this morning also talk about different architectural opportunities for a Memristor. So we are very interested in that, and so we fully agree with the philosophy behind the HP work, namely that if you have a new kind of device, maybe you don't want to force it into existing architectures, right? What existing devices do best, but you might want to look into what else they might do, and so take cues from nature, so to speak. You have a device which gives you a certain performance, and you want to build an appropriate architecture around that. So this, and I'm trying to make up some time with Pinaki. Pinaki, one of the things that I learned early on, since you're sponsoring this workshop, I learned about the golden rule. He who has the gold makes the rules. So basically, the CNN architecture, which is based on papers by Professor Chua and Yang, which were published in '88, is essentially a two-dimensional, neurally inspired architecture. So what you have is a network of processing elements, and each of these processing elements connect to nearest or next nearest neighbors in certain fashions. Those of you who are familiar with neural networks, you can think of those as synaptic weights. Obviously, a two-dimensional array like that is going to map neatly onto image processing applications. So for a given template, or you can view a given interconnection pattern as a template with which you might do image processing functions, right? And so the image processing applications or vision applications are natural applications for these kinds of architectures. There has been a tremendous amount of work done also on implementing this kind of architecture, and I think this is really what differentiates Professor Chua's CNN work from what people have done on CNN or on neural networks. It's not just simulations and then extrapolations, but there actually have been circuits designed and chips built. And I'm going to tell you a little bit more about this. So what's at the heart of these CNN arrays is an analog circuit. Essentially, the state of each smart pixel is represented, or this is the state of the neuron, if you want, is represented by a voltage on a capacitor. And so the way that the interactions between the states of neighboring elements, in other words, voltages at different cells, interact with each other are these voltage-controlled current sources. So in other words, depending on the voltage of the neighbor, more or less charge is pumped into the central element, which changes the voltage on that central element, right? So in this way, you can implement near-neighbor connectivity. The trouble with implementing structures like these, or what's taking up most of the area on the chip, are these voltage-controlled current sources. And so I believe, and I'm going to say a little bit more later on, that there might be an opportunity for Memristors to function as programmable synaptic weights, so to speak, from one element, from one cell to its neighbors. But so just continuing the CNN story, a few years back, well, it's about 5 years back now, in particular, a group in Seville in Spain designed a 128 by 128 array where each cell contains not only transistors, processing elements, so these interconnection weights, these voltage-controlled sources that I mentioned before, but also a photodetector. So you have an incoming flow and a visual flow where sensing and processing is concentrated within each element in this special purpose processor. This allows you to do image processing functions extremely fast with a small area of silicon and with small power. If you were to compare the equivalent operation that you can get out of a CNN chip like that with what you would do with conventional workstations, you would need a large cluster of workstations to do that. Now, I want to make sure that this comparison is not completely fair. I mean, a large cluster of workstations can do much more than what the CNN chip can do. However, the point is, for certain applications, this architecture, the CNN architecture, can give you a tremendous performance advantage. And so just look a little bit closely inside this chip. So you have both analog memory, you have digital memory, you have analog logic and digital logic. You can appreciate it's not easy to design a chip like that. And so depending on how you set the interconnect weights from one element to its neighbors, you can perform different image processing functions. So the way that a chip like that is programmed is very different from the way you would program usually. Yeah. So the primitive elements are not Boolean logic functions like loops and so on, but it's really you program it by mixing and matching templates, right? So it's really quite different way of thinking about programming. Just as an example, and this is with the chip that I showed you before. So you can do image extraction operation in real time. There are much more demanding operations like that one can do. These chips function at speeds at clock frequencies of 10,000 frames or 20,000 frames a second, depending on the complexity of the algorithm. And there really is nothing else on the market that can do something like that. Of course, the price that you have to pay is you have to design this chip in the first place. And so Professor Chua's work, really, which started out as nonlinear circuits, has led, as I have showed you, to actual chips. And these chips have done very well. So in particular, they took first prize. There's a product which has two of these chips in the eyes. This is the so-called bi-eye camera, which was developed by a company which actually is housed here in Berkeley, just a couple miles down to the ocean off University Avenue, Utica's company. There's an existing collaboration, as I mentioned to you in the beginning. I'm not going to go into great detail on that, but we're fortunate to work with Professor Chua and this CNN technology in the framework of an ONR MURI project. Shagan Batar, who is in the audience, is behind this. And so just very, very briefly, what we're doing as part of this project is trying to develop new kinds of algorithms for CNN. This is the info part, if you want, of this collaboration. Another group at Berkeley, Professor Werblin's Vision Research Lab, is part of this collaboration. So they're looking at the early visual processing that goes on inside the retina. It turns out there's really quite a bit of processing that goes on right in the front of the eye. So you have a huge amount of visual data that flows onto the eye, and most of the processing is actually done right in the retina. And so this huge amount of incoming information by the retina is reduced to a trickle of information, if you want, which is sent up to the cortex, where some of the higher order processes are done. And so it appears, and Professor Werblin has used the CNN paradigm actually as a way of thinking about connectivity inside the retina. So there are spatiotemporal signatures that are being extracted from this incoming visual flow and then represented as features and sent on for higher order processing. And our part of this collaboration is to try to integrate in each of these smart pixels. As I mentioned before, existing chips already have photodiodes, which give you sensitivity in the visible and up to the near IR. However, there are quite a few applications for which it would be important to have sensitivity in the mid-wave IR and in the long-wave IR for fusion applications. You can imagine the military is quite interested in that. And so the challenge there is to come up with detectors, long-wave or mid-wave infrared detectors that are compatible with silicon processing, that you can integrate right in with the CNN circuitry. And so we've done work on nano antennas, which are sensitive in the long wave IR. So just sort of a bird eyes view of what's going on there. Okay, so trying to keep on time, I would just like to wrap up here my comments. This symposium actually, which might be the first in another conference series as we look back a few years down the line, really has been on memristors and how they might match or stack up in different areas. The area of logic, the HP group, has been talking about that. And so what we are trying to do is we're trying to include in our benchmarking effort, as we look at all kinds of new devices as part of the NRI, we're also going to include the Memristor in our benchmarking effort. And I'd like to mention those of you who are interested in this kind of work, as part of the next MIND review, there's going to be a one-day workshop at Notre Dame in August. August 18 to 20. We haven't quite decided yet what the date is going to be, where we're going to talk about this sort of the outcome of this benchmarking effort. Obviously, maybe some of the short-term applications of memristors might be in the area of memory. I have not commented on that. We had a beautiful talk by Professor Baser. I would also like to mention that in the audience here, there's Dr. Campbell Scott. I'm familiar with a review, a very nice review on a lot of the work that has been written on memristor type memories. And it's really, there's a lot of physics going on as we have heard. And so Dr. Scott has kind of cataloged a small zoo of IV characteristics that you can find in these kinds of structures. It's really fascinating physics that's going on here. And then I've also mentioned, and you've heard from the HP group, that these kinds of devices might be used in synaptic type functions. So what I have in mind is that instead of having voltage-controlled sources, which you can change the weights, right? The weights with which neighbors connect with each other. You could have memristive type elements. However, these memristive type elements would have to be different from the ones that we have talked about so far. So if I understand things correctly, so far they function mostly as switches, right? So you pump current through, some internal state changes, and then at some point the switch from one, say from a high resistance state to a low resistance state. However, in principle, it seems to me what might also be possible that you have an analog version of that. As you pump more and more charges through, the resistance changes in an analog fashion, right? So that the resistance that you measure is actually a summing function of the charges that you have pumped through. And if it were possible to realize devices like that, I think that they would come in very handy in neural or CNN type circuits like that I've talked about. So I think I'm going to leave it at that. Again, it's a pleasure to be here, and I would like to thank you for your attention. Thank you.
So Porod finished a little bit ahead of his time, so we can entertain a couple of questions if you do have any questions.
Maybe Pinaki wants to talk a little bit more.
Any question? Yes, sir. Yeah.
I'm sorry.
Yes, there's a question. Yes, sir.
It's a just comment. There are devices where you can change resistance pumping current.
Can you repeat the question?
Yes, thank you.
Please repeat the question and answer it.
I'm sorry?
Can you repeat the question and answer it?
The comment was, there are devices where you can change the resistance by pumping through current, right? Yes, thank you.
Any other question? Otherwise, thank you very much.
Thank you. Oh, thank you. Thank you. Thank you, Steve. Yeah, I'm going to take it.
So while we are changing the computer, I'd like to introduce the next speaker, who is Professor Massimiliano Di Ventura. He is a professor of physics at the University of California, San Diego. Yes, he earned a PhD in physics from EPFL, École Polytechnique Fédérale de Lausanne in Switzerland. And his research field includes theoretical condensed matter physics, transport theory, materials science, biophysics, electronic and optical properties of semiconductor heterostructures. Thank you.
All right. Well, let me see if it works. Okay, I'd like to, first of all, thank the organizers for inviting me here. It's been really, really interesting, and I learned quite a lot. It was actually funny to get an email from the chancellor from UC Merced. I thought that something was wrong, but then I read along and wasn't anything bad. You know, you never know. Anyway, so thanks again for this very nice invitation. And actually, I must confess that I've been ignorant about Memristive systems and Memristors until the Hewlett-Packard group published this. We saw, in fact, some of the characteristics that you've seen before, but we never cataloged them in terms of Memristors. So as soon as we saw that paper, as soon as I saw that paper, I actually went back into the literature and found Professor Chua's papers and Professor Kang's papers. So it was nice actually to put a name on certain things that we were looking into. And in fact, some of the things that we've been looking at were spin-dependent transport in semiconductors. And actually, I was intrigued by a paper that came out last year on amoebas that actually can learn, actually can recognize patterns. And I will explain you how, in fact, you can use Memristive ideas to explain such things. In fact, one of the guys that was in that paper this year won the Ig Nobel Prize, you know, this fancy Nobel Prize for strange research or weird, however you want to call it. Anyway, I want to acknowledge my collaborators. Actually, Steve LaFontaine is an undergraduate with me and worked really well on amoeba's work. Yuri Pershing was a postdoc with me, and now he's actually a professor in University of South Carolina. And so I will briefly re-mention the definition of Memristive systems because it pertains to what I'm going to talk about. It's been discussed already, so I don't need to go into details. And then I will talk about memory effects in spintronics and learning circuits and amoeba's learning. These are the topics. In fact, I'm not an engineer. I'm a theoretical physicist, so it's worse than an engineer. And so my interest was really understanding fundamental physical processes in spintronics, for example. And couple this also with amoeba's learning, as I will show you in a moment. So let me go back to this definition, which we saw this morning, beautifully explained by Professor Chua, in fact. And here I describe the most general class that is Memristive systems, current control Memristive systems, where you have a relation between the voltage and the current, and the resistance, which I call, indicated with M, just to say that it's a Memristive system, depends on a set of end-state variables. So as it was said this morning, it could be anything. In fact, what I will show in a moment is that these variables could be the spin polarization, in fact, in semiconductor spintronics. And these state variables have their own equation of motion, and this is the general definition that was discussed in this paper by Chua and Kang in 1976. Now, the Memristor, as it was discussed, is just a special case of this, with the resistance dependent on the charge in the device. And clearly, the charge is related to the current via the derivative in time. So this is, in fact, the systems I will be discussing belong essentially to Memristive, to the Memristive definition, not to the Memristor definition. So the most general class of systems. And so let me go to memory effects in spintronics. So you, as you probably know, right, there is a possibility to build devices using, instead of the charge, the spin degree of freedom. This is another possibility. And people have thought about these devices. In fact, there is much discussion about spin transistors in literature. And people have, most of the time, looked at so a spin transistor would be made of some, let's say, a semiconductor and some ferromagnetic, two ferromagnetic materials at each ends. And you are trying to inject spins on one side. These will travel, possibly will actually, their polarization will change according to some external parameter. And then you will collect them on the other side. So this is a general principle. Now, people have looked mostly at the spin injection mechanisms. In fact, the difficulty of injecting spins is notorious. But there is also, if in any functional device, you would also have the opposite process, which is a spin extraction. You have to take the spins out of the system, not just bringing them into the system. It seems, naively, one would expect that these two processes are specular. So essentially, the spin injection would be essentially the same as the spin extraction. In reality, they're not. In fact, I'll show you in a moment that there are phenomena that occur here, which are in fact memristive in nature. And so I will focus mostly on the spin extraction, so the interface between a semiconductor and a ferromagnet. Now, here also for analytical purposes for what I'm talking about, it's not necessary. I'm thinking about a half metal, so a perfect ferromagnet that has 100% polarizability. The conclusions would remain also if this is not a perfect ferromagnet. And here I'm assuming also a semiconductor. And I couple this interface to a circuit, and I drive current into it. So if this is a half metal, so an electron with spin up would go there, but an electron with spin down will be stuck at the interface, right? Because it cannot go through the interface because it cannot be collected by the half metal, by the ferromagnet. And so after a while, you start to have a lot of these spin-down carriers that accumulate at the interface. So you create a sort of cloud of spin-down electrons. And due to Coulomb interaction, they will start to blockade the flow of the spin-up electrons. So the spin-up electrons all of a sudden see a cloud of spin-down electrons, and they are repelled from this cloud, and so they cannot go through. So you would have an effective blockade of the current. So we have described this using spin diffusion equations. I write them here because then I'll show you that, in fact, that they are memristive in nature. So you have the usual equation of motion for the density of spin up and down, related to the divergence of the current density up and down. And then you have a relaxation term that allows spins to actually flip from one configuration to the other. And then you would have also, the current is related via the usual electric field, and then you would have also diffusion term in the semiconductor. And clearly you have to satisfy, all other conditions of electromagnetism on this. So if you try to solve these equations, in fact, by assuming that at infinity the system is spin unpolarized, and then you look at the condition at which the current actually is blocked, you will start to see that by increasing the bias, the density of spin down electrons, in fact, start to increase. And so you start to block the incoming number of spin up electrons. So all of a sudden, you would have a condition in which the spin up electrons will be 0, and the spin down electrons will be 0. The interesting thing is that under those conditions, and if this is a metal, you can actually calculate this analytically, and you get the critical current at which, and the critical field at which this appears. In fact, it can be realized in practice. Here are the numbers, for example. This thing, as I said, would block the flow of electrons according to whatever is the resistance here. And this, in fact, can be used, for example, as a current stabilization device. So this is a possible a possible application. However, we're not interested on this here, but we're interested mostly on the memristive behavior of this thing. So let's suppose that you start changing the voltage in a non-linear way. And so from a usual conductor would respond like this, right? You would have a current that follows the shape of the bias. In reality, what you would see in this system is that the current shows spikes actually at these jumps in the voltage. And these spikes are essentially the memristive behavior because it takes a time for the polarization to adjust to an external voltage. And so according to, with a competition between diffusion and the relaxation processes. And so it is this, in fact, adjustment of the polarization field inside the semiconductor that gives rise to these spikes and gives rise to these memory effects. In fact, if you look at it from a formal point of view, you see that the voltage is in fact related to the current via internal parameters, which essentially are the spin polarization of it's a spin polarization of the system, with which follow its own dynamics. So this is formally, and that I must confess I discovered it later, it's formally a memoristive system. And so that can be classified as a spin memoristive system. In fact, if you look at now at the IV characteristics of this, so you would see these famous hysteresis loops. They cross 0, so when voltage is 0, the current is 0. There is no energy storage in this device. The other interesting thing that was discussed before, a very small, very low frequencies, this behaves like a nonlinear resistor. And increasing the frequency, you start to broaden these hysteresis effects. I don't have the plot here, but at extremely high frequencies, essentially, there is no hysteresis. The system behaves like a linear resistor. And this can be understood from physical grounds, right? By increasing the frequency enormously, the spin polarization doesn't have time to adjust. And that's the physical reason why this happens. So this is an interesting result that I said we could put now into the context of this definition. Another one which actually has get a lot of attention lately is the spin Hall effect, the equivalent of the Hall effect, but for spins. Now, suppose you have a semiconductor. Don't look at this yet. Okay, suppose you have a uniform semiconductor and you drive current into it. There are intrinsic, for sure, spin-orbit interaction is always there, mechanisms or extrinsic mechanisms, so that the spins will be deflected according to their sign. So the spins, let's say, up will be deflected in one direction, and spin down will be deflected in another direction. And so at the edges of these, so if the current goes in this way, right, if you have, sorry, the field in this direction, you will accumulate spins of one polarity on one side and spin of the other polarity on the other side. This is the famous spin Hall effect, which in fact has been verified also experimentally. However, if this is uniform, so the density of charges is uniform all over the place, then the charges that go in one direction cancel the charges that go in the other direction. So you do have an accumulation of spin polarization at the edges, but you do not have a charge accumulation. Now, this is a problem in general because measuring spin polarizations is way more difficult than measuring voltage, voltages. And so what we thought is the following. So how can you actually measure a voltage in a system like this and so show that you have a spin Hall effect? Now, you can do it by simply changing the density transverse to the direction of the field that you have here. By doing that, then all of a sudden, so suppose you have just either smooth profile or a step profile, doesn't matter. You can do it with a gate, you can do it by doping, you can do whatever you want. The important thing is that you have an asymmetric configuration of charge density in the transverse direction compared to the field. Now, all of a sudden, if you now drive with the field currents, not only you have a spin deflection, which could be, again, intrinsic or extrinsic, but you would have also a non-compensated current that goes in the opposite direction. So all of a sudden, you start to accumulate also charges. Here I plot the extra charge compared with the zero field. And you start to have these huge spikes of charges. These are for two different profiles of the charge density. So one that is step-like, and the other one is exponential. So the decrease is exponential going from one interface here to the other, surface to the other surface. So what you, the charges essentially accumulate at the edges. This is similar to the local resistivity dipoles you have, in fact, in nanoscale systems, and you do have, in fact, a transverse voltage. Now, the difference, the major difference with the usual classical textbook Hall voltage, which would actually go linearly, right, with the driving field, this voltage is quadratic. So we can prove analytically that this voltage is quadratic with the driving field. So that is an interesting difference compared to the classical Hall voltage as you find in textbooks. In fact, with this thing, so before I go there, you can actually show that you have frequency doubling, like a second harmonic generation using this device, simply because you have a quadratic term in the Hall voltage. Now, that's not the Memristive behavior I want to discuss. However, it's an interesting byproduct of this spin Hall effect thing. So what we actually looked at is, suppose I now take this bar, so what I have here, and instead of having a fixed bias, I have a time-dependent bias here, and I look at the IV curves. So what you find are interesting, in fact, shapes, all possible shapes. So you have this hysteresis type of loops. You would have a very low frequency, again, not much hysteresis. And here, in fact, you can see a very large frequency, also not much hysteresis. And the hysteresis here is, again, the same as you had in the previous spin blockade device. It takes a time for spin polarization to respond to a change in external bias. So this is an interesting, again, this is another example where I couldn't put here the equations because they're huge. So I couldn't actually show that this is a Memristive device in terms of its definition. It's a very, long equations. This is what you were saying, right? That sometimes, you may have it, but it's not so simple to show it analytically many times. In this case, it's very difficult. You get this curve, and if you want to show it analytically, you have to go through a lot of math. But trust me, in this case, we actually could prove this. OK, so this concludes my memory effects in spintronics, and I go to the last part of my talk, which is on amoebas learning. And this intrigued me a lot, in fact, when I read this paper. And if you go back to previous papers, actually, people have shown that not only amoebas learn patterns, like I will show in a moment, but also they can solve mazes and all sorts of things. So there is they show interesting behavior. I don't know if you want to call it intelligence. It's not definitely the intelligence we talk about. Not definitely cognitive intelligence, but it's some form of adaptive behavior. So for the following, I will discuss only this particular case, which intrigued me a lot. This is a cartoon of an amoeba, which so the blue is essentially the liquid where it stays. And in fact, it's a blob, right, with lots of, how you call this, kind of holes, right, in the blob. And in between the holes, you have these channels that actually where the fluid, the endoplasm, which is called actually sol, flows. It's a low viscosity fluid that flows, and they are surrounded by an ectoplasm, which is a gel, which has a much larger viscosity than the internal sol, so the internal endoplasm. And so how does this move? The rhythmic motion is determined essentially by biological oscillators. These are all over the place, right, or even in our bodies. And so these biological oscillators, essentially, they contract and expand these channels, which push the liquid essentially inside, giving the motion to the amoeba. So far, so good. The point is that if you try to, so these unicellular organisms live in normal conditions, let's say, at a certain temperature, a certain humidity. If you change the temperature abruptly, okay, the velocity of the amoeba actually will slow down. They will slow when the temperature is dropped. So this is an unfavorable condition, and the amoeba will slow down. Then in this experiment, this was done 3 times at regular intervals. And the nice thing is that when these, and so the amoeba every time would slow on average its motion. And so when the 4th pulse should have been there, right, the amoeba actually continued to slow down as if it remembered this pattern of pulses. So this is an adaptive type of behavior. So again, these researchers have tried this, and then by lowering the temperature at regular intervals, and the amoeba will remember actually that it has to slow down in correspondence to the next impulse, okay, so a stimulus. And then if they wait not too long, sometime, but not too long, and they repeat this with just 1 pulse, the amoeba that has been trained, so the one that has received these training pulses, will actually respond again as if it has remembered that the pulses should occur at that period of time. Okay, so this is a very complicated problem, so there is no hope you can actually do it from microscopic point of view. So my idea was, okay, let's try to have a circuit analog. And at the beginning I thought, well, we need a nonlinear element. In fact, then I discovered after the HP guys published their paper that this could be given by the Memristor. And let me tell you, however, in order to, so clearly you can now transform this into a Memristive circuit. However, you have to identify what is the mechanism that creates memory in here. So one possible idea, and there may be other mechanisms, so I cannot claim that this is the only one, but one possible mechanism which occurs is the following. When you change conditions, then these veins, essentially, these channels start to contract, okay? But under certain conditions, they may contract so much that the ectoplasm, so the surface of this, breaks down and becomes itself endoplasm. So it's like creating new channels. It's like creating new conductance channels in the titanium oxide. Here is like creating new low viscosity channels in a much more complicated organism like the amoeba. So this is what we identify as the possible mechanism for the memory. So the fact that under certain conditions, the ectoplasm can break down and create a new low viscosity channels, and so the motion will change in a nonlinear way. Okay, so it has some memory in it. Okay, so if this is the mechanism, and as I said, it may not be the only one, we know that there are oscillators. The biological oscillators are there. In fact, they determine the rhythmic flow of the amoeba. And so the control parameter in the amoeba is the temperature and the humidity. In our electronic circuit would be the applied voltage. The output signal in the amoeba is the velocity. For us is the voltage, wherever you want to measure it. Here we measure it at the capacitor. And the oscillator, the biological or biochemical oscillators for us is an LC contour. And then the memory element is what we identify as this gel-sol breakup inside the amoeba, which we model with a Memristor. And the parameter containing information it's for us the veins and the low viscosity channels in the amoeba, while it's the resistance of the Memristor which contains information on the memory. So we did this. We picked one of the most simple expression for a Memristor, which with the function here, whose time derivative would change like this in a nonlinear way. There's a threshold voltage, like an activation voltage, and then we simulated this thing. So if you send in arbitrary pulses, so some random sequence, what you see is that you don't train the circuit. In fact, the amplitude on the Memristor, the voltage on the Memristor is not enough to activate its memory. But if you send the pulses at the right frequency of the LC contour, then all of a sudden the amplitude on the Memristor starts to increase at every step until it passes the activation and it starts to remember. Clearly, we put also something that damps this thing. And so you would have nice oscillations. And in fact, so what we did is, OK, let's assume also that the maximum of the voltage is cut off. In fact, this is probably what happens in the amoeba. It cannot increase its velocity beyond a certain level. And this is the result. So suppose you have a training pulse. Then when you stop it, the circuit will still oscillate because, in fact, it has learned, okay, the pattern. And then if you repeat this after a certain amount of time, one time, then if it is being trained, then it will, in fact, remember. If you don't wait too long, right? It will remember, it will do what the amoeba does. In fact, it will repeat the pattern. But if you don't train the circuit really well, so let's say a kind of a random sequence, then the response will be very weak. And if you try to excite it later, the response after that is even weaker. So this is, in fact, it's a good model, let's say. Let's put it this way. It's definitely not the exact thing that happens in the amoeba, but it's a good model to explain how actually you have adaptive behavior in these simple organisms. OK, I think my time is up, and I just want to conclude. In fact, there are many more Memristive systems than what we've seen so far. In spintronics, in particular, the whole class of spintronic devices is probably Memristive in a way or another. Also, it is interesting to see that even memory effects in unicellular organisms and possibly even in more developed organisms are there and are probably responsible for many of the things that we see when we train them, for example. And this is an interesting area of research which we're trying to pursue. And so, along the lines of neural networks, how to expand this learning to much more complicated networks. And these are the references if you're interested in. And with this, I thank you very much for your attention and take any questions if there are any.
Thank you.
Thank you.
So if you don't have questions, we can entertain some questions. Any question? Yes, one question.
Can you eradicate the voltage using
Sorry, I didn't get the question again. Can you repeat?
Multi-bit state using the Memristive spin system.
Oh, if you can do that, you're saying. So if you can use spin Memristive systems to have multi-bits. Well, that I haven't thought it yet. But if you combine them, you're saying, together, maybe it's possible, yeah. I don't know, though. I haven't investigated that.
OK. Any other question? Oh, yes, in the back. Yes. Could you speak loud, please?
So the amoeba learning, it can only learn one pattern. Is that correct?
Yeah, that's what they found, yeah. Only one pattern.
So then you can teach it a second pattern and it'll repeat that one.
That's correct, and nothing else. Oh, it's a unicellular organism. You don't expect too much.
Okay, thank you very much. In
Thank you.
appreciation, I will want you to give this one to you. Thank you.
Let me just.
Before taking the break for poster session, we have one more speaker. His name is Blaise Mutay. He is a graduate student at the George Mason University in Virginia, near Washington, D.C. area. And Blaise is going to talk about the proposal for Memristor crossbar design and the applications. Blaise has a very interesting background. Although he's a graduate student, he's doing lots of pattern analysis. So he works for U.S. Patent Office. Used to.
I'm a patent.
Yeah, pattern analysis. Right, thank you.
Okay. Is this? Okay. Oh, okay, good. First of all, I'd like to thank the organizers. I'm a graduate student. I'm not as esteemed as the earlier presenters, so I'm especially grateful that they'd invite me to say a few words about Memristor crossbars. I have a little bit of a different perspective. I'm more application-driven than science. My background, my first year in the undergraduate, I majored in physics. But once I figured out I couldn't make any money, I changed to electrical engineering. Okay. One of my focuses is finding desirable manufacturing goals to ease the adoption of Memristor crossbars by universities, fabs, pretty much everybody, so that it could very rapidly be adopted to develop new applications that can help accelerate the economy and repair some of the damage in the last couple of months. Basically, design should be compatible with standard manufacturing techniques to facilitate wide use and experimentation by many participants, universities, research labs, existing fabs, without a significant investment in new equipment. The design should be easy to integrate with standard electronics components and materials. The design should incorporate materials capable of the high resistance of the memristor. The ratio between the high and low resistance should be very high. Design should be robust to both temporal and spatial variance of the memristor. That is, over time, the memristor should stay the same, and between different cross points, it should be relatively constant. The average should be pretty uniform. Design should avoid internal feedback current paths in the crossbar, which can limit the speed and the ability to read the resistance states reliably. And the design should also ease reconfiguration of the resistance states. While HP has the nanowire designs, which may be very good for RAM. There's some applications which we could just use microwires and to get it more put it into use more quickly, especially in applications in signal processing and pattern recognition, which you'll see as in future slides. Okay. And also, nanowire defects in addressing are significant problems which might slow down the implementation. Okay, this is an example of the problem of feedback paths in the crossbar. Now, suppose you want to read the high resistance junction that's in the second row, first column, and you have transistors connected to the input outputs. Basically, you input a 1. Basically, you want to read that high resistance junction as a high resistance junction and not a low resistance junction. But what will happen is you get a feedback path and you don't get the right reading. Now, a simple solution compatible with microfabrication techniques is the incorporation of p-n junctions in the crossbar, which was originally conceived by Stanford Ovshinsky for phase change crossbar memory. One variation of the solution adapted to bilayer oxide membristance films is as follows. You start with a silicon wafer, have a silicon oxide, deposit a metal layer, p-doped polysilicon, n-doped polysilicon. You etch out the aluminum P and N doped layers, fill it with silicon dioxide, then deposit the memristive layer, then with a platinum, then pattern the platinum wiring on top, perpendicular to the bottom aluminum wiring. The bottom aluminum wire would serve as the columns of the crossbar, while the platinum wire will serve as the rows. Now, for applications, some desirable goals is to complement, not conflict with existing technologies and markets to achieve ease of acceptance. You don't want to compete with Samsung, Micron Technologies, Infineon, and the dozen other companies that are developing other solutions to non-volatile memory. What you want to do is identify small markets that have the potential for exponential growth by developing just markets that didn't exist before. One example is FPAAs, field programmable analog arrays, which is somewhat similar to field programmable gate arrays, except instead of working with logic circuits, they're working with analog circuits, filters, control systems, and so forth. Commercial robotics. Commercial robotics is another application area where you have companies such as iRobot that is building a vacuum cleaner that basically it identifies everything around it on the floor, and it could basically clean the floor without you have to do anything. So that's kind of an interesting application. Neural interfaces is another application. I think a few weeks ago, 60 Minutes did a piece about a monkey who had implanted neural electrodes used to control a robotic arm. That's kind of it's kind of difficult to implant these types of electrodes in the human head without. So that area is more for biomedical applications, but there's also a company called Emotive, an Australian company that's coming out with an electrode array cap, which you can use to control a video game avatar. I think they're coming out with it in December next month, so it's kind of a cool application area. Okay, what you also want to do is solve problems that conventional electronic hardware and software do not provide efficient solutions, but which Memristors can, such as pattern recognition, the traveling salesman problem. Okay, one circuit element which could be very useful to achieve these goals is the operational amplifier. Now, the operational amplifier is a very simple device. This is an example of the implementation as a summing amplifier, where you have a feedback resistor coming into the inverting input from the output, and you have input resistors also coming into the inverting input. Now, the output in this case, the output voltage would be the summation of each of the input voltages weighted by the ratio of the feedback resistance to the input resistances. Now, this kind of design can be combined with Memristor crossbars as follows. Basically, you have a Memristor crossbar, you have resistors coming into the input columns, and you have the outputs connected to the inverting terminal with the feedback resistor. Now, the analysis for this type of construction is as follows. The feedback current will match the summation of the currents coming out of each crossbar junction. And basically what you get if you follow through this analysis is that the output voltage is a summation of the transfer function, which is a function of the memristance values, times the voltage inputs. So okay. Now what you want in this type of equation is for the voltage states to have binary values, so you could put the voltage to a low level, a high level, which is commonplace in electronics. But you also want that same property for the transfer function. The transfer function could be set to 0. Ideally, you would want to have ranges between 0 and 1 based upon the memristance values. It's not so hard to achieve that for having the transfer function having a value of 1 by setting the input resistances to a value of equal to the feedback resistance minus the average low value of the memristors. However, the high value, for the high memristance value, it's not able to be 0 because that would require the feedback resistance to be 0. You're not going to get any signal transmission at all. So basically, you're going to have to deal with a low bit error. And the tolerance for that low bit error can be set in terms of the high value of the memristance and the low value of the resistance and the feedback resistance in that equation. Equation right there. Solving for RF, basically you get upper bound to the feedback resistance. So basically you have an upper bound. Okay. Now you also have to take into account variations in the memristance due to temperature variations or other effects. Basically that's what I'm doing with these equations, taking the derivative of the transfer function and setting it less than the maximum allowable bit sensitivity. And basically, if you work it through, you get basically a range of values for which the circuit will work fairly well, dependent upon the variation in the memristance and the sensitivity. And one thing you can do to, okay. One possible rule of thumb for this type of analysis is to set the variations dependent upon the number of crossbar columns. If you have 100 crossbar columns and you have a bit variation of 1 over 100, then the total, if you sum them all up, the total bit variation will be 1. And if you're dealing with a 100-bit system, it's 1 over 100, 1 bit variation, depending on the application, could be tolerable. So this basically, taking this equation, forgetting about RF for a second, you get it, and assuming a large n, it reduces to that equation. So that basically gives you your tolerable variation of memristance that you want to consider for 1-bit errors. If 10% of your bit errors are permissible, then it would reduce to this equation. So so if it was 10%, n over n would be 0.1, or small n over big N would be 1. Okay. Now we'll go through a couple of applications of this type of technology. First off, programmable drive waveforms. Okay, in many electronics applications, variations of circuit parameters due to temperature change, aging, etc., require an adjustment of the drive waveform. For example, LEDs, they require higher amplitude voltage drive over time to produce a consistent light output. Another example, waveform adjustment is desirable in different applications. For example, inkjet printheads. In order to change the resolution, change the drop size, you want to control the amplitude and the pulse width. So basically, it's desirable to have a simply implemented system to do those types of functions. Now, for timing modulation and amplitude modulation implemented in hardware, complex circuitry might be required, and it has a limitation in the number of possible waveforms that you can produce. Now, for software-based solutions, you have more versatility, but you have to fit an entire microprocessor, which you might not want to miniaturize. It might be too costly. This is an example of a circuit which could be used to form a large variety of different waveforms by programming the Memristive states using binary values where the closed circuit connection, there we go. Closed circuit connection is indicated by the black dot. Open circuit connection is indicated by pretty much an open circuit, pretty much the same schematic type thing. Okay, and basically you have a shift register that shifts a binary value through the outputs a logic value to a voltage level converter that converts the logic value to a range allowing a range that's lower than the Memristor's threshold, so you can basically transmit current without significantly altering the Memristor state. Now, by selecting, which types of Memristors which junctions are on and off, altogether you could have a maximum of, 2 to the 16th is 64,000 possible waveform combinations. Okay, and basically using the resistors by ranking them at ratios of 2, you can control the amplitude depending on which memristance row is selected, and selecting the columns controls the timing basically. So in this example, as the bit shifts through, you're controlling the amplitude. So you get basically a staircase type pattern at the output. Okay, the advantage of this type of design is both timing and amplitude of the output waveform can be adjusted by binary switching of the memristor states of the crossbar. Okay, even with only binary memristor switching, a very large number of possible drive waveforms are available. For example, 10 by 10 crossbar can give you 10 to the 30 states. It's pretty significant number. Okay, combined with techniques such as hill climbing and genetic algorithms, this has a potential for generating self-optimizing waveforms for real-time adaptation of circuitry to effects of aging and temperature variations. Okay, potential application number 2, pattern recognition. The problems with conventional pattern recognition solutions, software-based solutions require time for data transfer between memory and processing circuitry, which causes a lag in responsiveness. Hardware solutions can be faster, but have limits in adaptability and limits in the range of patterns that can be classified. Memristors offer a route to a morph-ware pattern recognition solution, combining both memory storage and data processing in the common circuit. Okay. This is an example of a circuit architecture for pattern recognition. So basically, you have a series of inverters on one side, no inverters on the other side, and again, the same voltage level converter circuitry. In this case, the voltage level, basically you implement that with the variable resistor and a few transistors, not that difficult. And adjusting the variable resistor, you could amplify the voltage above the threshold for memristance variation. So basically, you're inputting a 1010 that gets sent to the crossbar to the selected row wire through the feedback resistor. So basically, you're setting each row one at a time. Now, when you're finished setting all of the states, what you can do is then you could switch the voltage level converter from greater than the threshold voltage to less than the threshold voltage, so you're not going to have much variation in the memristor states. So basically, when you're doing it, when you do this, the similarity between the voltage binary states and the memristance binary states, high or low resistance, are basically compared, and the output current, the magnitude of the output current flowing through the feedback resistor is dependent upon the similarity between those two binary patterns. And the second op amp is a comparator, which you can put a voltage reference into the non-inverting terminal and use that as a threshold for determining how sensitive you want the comparison. If you want, you could set it so that you could get 5% bit error, 10% bit error, and so forth. So basically, you see that in the first example, there's only one bit match between the voltage state, input voltage state, and the rows. Basically from the third column, because there's a low resistance there, and there's a high input resistance, so that'll pass current through there. Meanwhile, at the output of the inverters, you get 1, 0, 0, 0. So there's no, basically, there's zero. The only input having a voltage is the leftmost one, and the resistance state there is high, so you're not going to get any current. So it's only going to be 1 unit of current. Meanwhile, in the second row, basically it's identical. The resistance states have the same pattern, bit pattern of resistances as the voltage states. So basically there's identical matching, and you get 4 units of current flowing through the feedback resistor, which so the output voltage there will be 4I times RF, and compared to the VREF, it will be a higher value. Okay, and basically it's similar for the third row and the fourth row. So basically, the advantage of this type of design is the output voltage from the first op-amp is analogous to the exclusive NOR operation, whereas instead of dealing with single bit states, which only have binary values, the transfer function basically it's basically a summation where the output is a current level, not just a binary value level. And tuning the voltage reference can adjust the sensitivity of pattern comparison and adjust allowable bit error between resistance states and voltage states. Allowing for bit error could potentially be very useful in applications such as facial recognition, which can require robustness to a large percentage of bit errors. Okay, potential application number 3, FPAAs. Okay, the problem with conventional FPAAs are Motorola has a startup, I think they founded in 2000, 2001. But basically, they're simple reconfigurable systems which have only the binary states for the reconfiguration. They're useful for communication and control system applications by making adjustable low-pass filters, high-pass filters, or integrators, differentiators, that type of circuitry. But basically, they lack the ability to electrically tune the resistance, such as provided by Memristors, to achieve intermediate frequency states or pole zero adjustment. This is an example of a circuit architecture, basically that puts Memristors, a Memristor crossbar in the junctions between a set of, between a capacitor array in the feedback loop and a capacitor array in the input loop. And by tuning the Memristance values, you could basically tune a high-pass or low-pass filter to a variety of different cutoff frequencies. This type of design could be cascaded with another similar design, so you can create a band-pass filter or put in parallel with the design to create a stop-pass filter or a PID controller, or a variety of other circuit architectures. I basically just discussed all that, I think. Okay. Potential application number 4, arithmetic optimization problems. Now, the arithmetic systems that we have now are very good for what they do, which is unique processing of binary values where you're getting an exact solution. But the problem of segmentation between memory and processor circuitry, which has been around since von Neumann, can create a bottleneck in speed. New clock-independent designs are desirable. Basically, logic-based arithmetic is inefficient for some network optimization problems, such as the traveling salesman problem involving repeated recalculation of sums. This is an example of a circuit architecture that can be used for optimization problems, where you're basically using each row represents a bit significance value, and that bit significance value is determined by the ratio of the feedback resistor to the input resistor. For example, in the first row, it's R divided by R, which is 1. In the second row, it's R divided by R over 2, which is 2. The third row, R divided by R over 4 is 4, 2 to the 2. The last row, R divided by R over 8, which is 2 to the 3rd power. And basically, you could change the summation of which binary states you want to add together by changing the input to the column, the input voltage levels to the columns. So in the first example, you have a representation of binary 2 plus binary 4. And by changing the voltage levels, you could change it to 1 plus 3. Okay, so basically, this type of circuit has a problem. Op amps are slower than logic circuits, although you can have, there are still relatively high speed op amps that you can get by sacrificing the gain, the open loop gain. But basically, what the main advantage is you have less reliance on the clock for processing. Okay, and this type of design can be scalable to provide real-time solutions to network optimization. For example, in a traveling salesman problem with 100 nodes, including 5,050 interrelational distances, each distance metric can be stored in a different crossbar column, and comparison between different paths between the nodes only requires changing the bit pattern input to the crossbar rows and detecting the analog level of voltage output. Potential application number 5, signal mixing. Okay, the problems with conventional modulation systems is basically there's an increase in portable wireless electronics in the last 10 years, and that requires a more efficient use of spectrum with techniques such as frequency hopping. And another problem is encryption. You want to have a more secure encryption technology. This type of application basically requires 2 signals to be input. So there's a modification in the manufacturing procedure. So instead of having just that one PN junction layer, you have 2 PN junction layers, which basically you're sandwiching together the two, you're sandwiching the memristor between the 2 PN junction layers. So you'll have one input path formed between the aluminum, the platinum inputs, the platinum wire column outputs. You're not going to see me pointing on the computer. Okay, you have one input path, for example, going from platinum, the platinum wiring here. It could go out to the aluminum wire, going through the PN junction, and you have a second path, platinum, going down to the aluminum. Now this design, it reintroduces the problem of feedback paths in the crossbar, because you have the platinum here and the platinum here, which you can get feedback paths in there. But you have the advantage of reconfigurability that's offered by programming. You could program it one way and then program it the other way, because you have 2 inputs. And it has another advantage in the for signal mixing, is basically this little schematic shows. Basically, this is the. Oh, okay. The voltage, the Thevenin equivalent voltage here is a function of both the memristor state and the input voltage B and the input voltage A. So basically, you could have a signal of voltage input A, and a second signal, or a signal of voltage input B, a second signal of voltage input A, and those 2 signals are modulated based upon the memristor value and the values of the voltages, the signal voltages. So in this type of design, you could have a series of signal input voltages, a series of voltage modulation voltages, and you could translate how they're modulated together depending on which memristor values are in the on state, in the low resistance state. You could switch between, so you do like a communication signal. Basically, you're mixing the signals. So you can do an encryption algorithm that determines which crossbar states are on and off. Okay. The advantage of this type of circuit architecture is that switching the carrier frequencies allow more efficient use of spectrum and compensation for crowded channels. And the potential exists for improved signal encryption by sharing a randomized memristor switching pattern between the sender and receiver. Potential application number 6, artificial intelligence. Okay, now there are 3, the way I see it, there are 3 main routes to strong AI AI using Memristor crossbars. Neural networks is one. Genetic algorithms is another, where basically you're using selection, crossover, and mutation of the Memristor states to basically, for example, as I discussed in the first, for creating an adaptive waveform or some such application. The third approach is emergent complexity from memory prediction framework, which is discussed in a book called On Intelligence by Hawkins. He basically touches on this type of methodology. And so basically, how this could work is basically you have a summing amplifier connected to each row, and it sums the Memristor states and the voltages, feeds it back to, we'll get to where it's feeding it back to in a moment. Actually, so yeah, feeds it back to a second, the V2, V2. So they come out here, and they go back up here, and they feed it back between the two crossbars, back and forth. And you also have a series of sensors that are connected to differential amplifiers that compare the voltage levels, and you select one. I think I keep doing something. Okay. You select one row at a time, so that you basically keep resetting it and keep. So basically, it's a design. This is basically just a conceptual idea of how it could be implemented, but they're all of these are conceptual ideas. By the way, but I need a prototype for crossbar. Okay, but so basically they feedback one another, and you can have the Memristor pattern, which grows and changes based upon the sensing voltages, and you have output voltages that can also, that could change based upon the Memristor's voltages as they're changing. Okay. Potential applications number 7 and 8, neural interfaces. I don't think I'm going to have time to cover these, so I'm going to continue this at NSTI Nanotech Conference and Expo, May 3rd through 7th, 2009, Houston, Texas. Okay. I'd like to thank the organizers and participants. Thank you for Dr. Wei Wang, the College of Nanoscale Science and Engineering, for information and feedback on FPAs and suggestion for error analysis. And thank you for Jeff Hawkins. And read On Intelligence. It's a very good book. Thank you.
Thank you. In appreciation, we give it to you.
Thank you very much.
You went through so fast, so many things, but I wonder whether there is any question from audience. Yes.
I don't know how to ask this question. I don't know whether you have ever built any electronics in your life.
Yes, in undergraduate we did electronics. we put the transistor.
Simply replacing everything in the crossbar, right? I think it's resistor networks and so on. The race conditions and a lot of these things will keep much more difficult than what you think. It's not a plug-to-plug replacement for a resistor. Okay. And it's not a regular resistor.
Yes.
Really
okay.
That fundamentals.
Yes. Okay.
Okay, thank you. Thank you very much. So thank you for your attention. So before we take a break, what I like to call your attention to is until 4:30, you have time to go around the posters. And then at 4:30, we will come back. And to me, the last session will be most exciting. We heard wonderful presentations, and now we are going to invite the speakers back to the podium and then exchange some idea with you so that we can find out what exciting opportunities can be developed for the future. So I hope many of you can come back after a poster session. Thank you very much.